Okay. So first, I'd like to thank SABR for providing me the opportunity to present this to you. Let's start because we don't have a lot of minutes together. So my name is Martin Rioux. Pronounce it like Engine Rioux from the Dodgers. So in French, R-I-O-U-X is like the letter Y. So I'm the founder of IDEALIS. In French, it's IDEALIS, but there's a practical translation to IDEALIS in English as well. So today I'm here to present you my research about how to use PITCHf to benchmark the Ether performance through data envelopment analysis. First, 1 minute about myself. So I'm from Montreal, Quebec, Canada. Yes, I was a big Expos fan. I'm still is. And how unlucky I was because from 2010 to 2013, you see what I have circled in the picture. That was my office. I was a few steps away of the Olympic Stadium. So just imagine if the Expos would have been still in town. Every single night almost I could have just after work use my private parking over the plant and just see a MLB baseball game every time. But the Expos were not there anymore, so I missed that. Just another interesting thing, on Thursday, September the 5th in 2002, it has been the smallest crowd ever in the Olympic Stadium, and I was there. So it's a rare event, but I was there. And believe me, 2,000 tickets sold, but we were less than 800. I tried to count everybody, and we were not 1,000 people inside. So now there's some hope, but for sure it's still only hope for now. But at least twice a year, it seems we'll have a few preseason games, thanks to the Blue Jays. So last year, for 2 games, when the Jays has welcomed the Mets in Montreal, we draw more than 96,000 people in 2 consecutive days at the end of March. So at least we have this to enjoy. And yes, I was there as well, obviously. Okay, so IDEALIS, it's a startup company that I've launched last year, more than 1 year ago. It's a very specialized little company for now. The mission is to provide performance benchmarking about a lot of different type of industries. The traditional ones are the one coming from the retail sector, the franchises, the bank branches, any sector where you have a lot of units, a lot of decision-making units that you need to handle to manage, hundreds of ones, thousands of ones. The specific methodology that IDEALIS is using is specialized for its data envelopment analysis. It's not my invention. It has been done, created at the end of the 70s. It's well known in the world, but when you do some Googling of it, Google Analytics of it, it seems that North America is behind the rest of the world about how to use that methodology. So I'm interested to see at least how many people here, if you raise your hand, at least get a kind of a small introduction about that methodology. Is there anyone that knows a little bit about it? Not much. I see even no hand at all. So you see, it's not well known. So my challenge today with less than 20 minutes is to kind of educate you about it. It will be impossible to discuss everything about the methodology. So I'll do a quick introduction of it, but I'll focus on the results, how to apply it to baseball. But for sure, I encourage you to know and learn more about it, because with the big data thing, the big data era that baseball is starting, I think that methodology will have several different applications in the sports industry, especially in baseball. So data envelopment analysis, we can call it as well DEA. It's a linear programming-based technique that is able to deal with presence of multiple inputs and outputs. That's the key thing here. Several inputs that matters for the industry, for the stakeholder, several outputs, and that single analysis with the help of linear programming, so there's computing calculation here, is able to handle all of it to do weighting of the variables to make sure that it creates a value that makes sense for the application we are doing. So it's very customizable. What I'm presenting today, it took me almost 3 weeks to work with it, make sure there's a practical value, to make sure that we get the right inputs, the right outputs to blend together to get a score that will make sense, and I'll show you how. Okay, so for today, to keep it simple, the score that we create, the very last line, when the DEA score equal to 1, that's the maximum score possible with that methodology. It means that the unit, so the score of 1 linked to a unit, it means that it's the optimal reality, it's the more efficient one. So in general, this is it. DEA versus regression. It's a very interesting comparison. I have a background in statistics as well, so I'm a lucky guy that is able to handle both of it. And I know a lot, and I have done a lot of multiple regressions. It's awesome when you're able to handle the residuals behind these equations. But there's a very specific difference between the data envelopment analysis method and the regression. That little graph tried to explain this quickly. So the regression line is more an average line. So you have a model, but the model will pass through all the points. It's an average situation. So it explains very well what's going on average about the variables you have in your analysis, but the data envelopment analysis is looking for the optimum point. It's looking for the frontier. It's looking for where is the best thing ever. Even if you have done this only 1, 2, 3 times, that's the maximum reality. So that's the key difference. So my vision of this that started the analysis, let's just to wait about it. So about baseball, I know, and I have tried. I have played with the data using multiple regression a lot as well. Multiple regression works very well, but because it's average value, when it's time to do some prediction, even by even, at-bat per at-bat, pitch per pitch, now you're going back to individual data. And now, even if you have something providing you information on average, sometimes it doesn't work very well to have predictable information with small sample size as well. So if you look at what is the maximum reality, and then you go back and do statistical analysis on the DEA score, now you're able to work with a lot more small sample size, and you get p-value that will confirm you significant differences as well. So I'll show you some example of this. The specific data envelopment analysis model that I'm using is called the BCC output-oriented one. So because you don't know anything about DEA, just for the record, this is the model that has been used behind the calculation, but it is looking to maximize the output. So in general, so that's the last one about the introduction to the method itself. The graph on the right, if you look at the unit number, the letter D, the unit D, you see that as an input you got a value of 4, and for an output of 3. But because in the data set there's another unit that it is the letter S, that with the same input has been able to generate more outputs, the DEA score for that very simple example with a single input and a single output, the unit D will be assigned a score of 0.6 because it is the unit D with the same inputs has been able to generate only 60% of outputs that another unit of the same group has been able to do. So it's very simple when it's one input, one output, but the reality that I will present in the next slides, you have multiple inputs, multiple outputs. So there's several dimensions. You're not even able anymore to see it graphically very well. So that's the mechanic behind. And since you have multiple inputs and outputs, the methodology is looking to maximize the score. So depending on the constraints you have programmed, you could weight your inputs and your outputs. So you could provide more importance to some inputs versus others, and that's the same for the outputs. So the linear programming is able to calculate the maximum score that we can assign to a unit. So if you get something that has a value of 80%, you know that this is the maximum score that unit can get. It's impossible to find another way to provide a better grade to that unit. So that becomes very useful for the following. So the last assumption that is important to understand today is that because it's a comparison of inputs versus outputs, and so for a given set of inputs, you want to maximize your outputs, it is important that the input in your data sets follow the rules or the assumption that if I get higher values of these inputs, this will generate no less outputs. So because of this, sometimes the raw data, you need to transform the input, because if inputs goes up, you need to have inputs that when they are going up, it is generating naturally more outputs or the same. So let's talk baseball now. So for sure, DEA, you need to go back, Google it, find some information. It's not easy to explain in 10 minutes. So now let's talk about the results. So I have applied this to a PITCHf data, and I forgot about that page. So the research objective of that analysis was to get an objective way to evaluate the hitter's relative efficiency, to regularly hit the ball well, given the selection and the location of pitches he has swung at. So it's very important to understand that now every unit that I was talking you about, now every unit is a single in-play batted ball. So for a hitter at bat, if you put the balls in play, you get a DEA score about how good that ball has been hit. And it is using inputs and outputs that has nothing to do directly with if the ball has been a hit or an out. So it is using data coming from PITCHf, and these data are as inputs are the start speed, the brake length, and I add to transform the brake length in another variable that follow the assumption that higher values of inputs should lead to no less outputs. And I have had to create as well another variable called the PXZ, that is a function of PX and PZ that are available in PITCHf. And the outputs are the batted ball value that comes from the batted ball type information available through PITCHf. So that batted ball value is just a numerical value translating if the ball is a line drive, a fly ball, a ground ball, or a pop-up. So the analysis will use these raw data, and let's say for a given set of inputs, so for a given speed of the ball pitched, for a given break length, and for a given location, the more the hitter is able to hit the ball as a line drive ball, and the more it gets a distance of it, you will get higher score of coming from the DEA score. So I've used the 2013 database to create the model, and I've then redo the same methodology with the 2014 data, and I'm showing you results about the 2014 data, but the generation of the model itself behind has been created with other data. It's kind of good practice in science. So if we look only at the batted ball in place, we got in the 2014 year more than 126,000 batted balls coming from all the games all year long. To convince you that DEA scores could be a very useful information that aggregates a lot of raw data information, I've done a few measurement system analysis, if you want, a specific one, but from the 126,000 data available, I did 10 different times I generated a random samples of 500 of these data, of these in-play ball, and I have run the data envelopment analysis, and I got these type of scores. And the way I've designed the weighting of all these inputs and outputs, I get to a point where there's a kind of a cutting edge around the 0.7 score. So to make it practical, you need to see of the score as if an in-play ball or an in-play batted ball get a value of 0.7 or more. Look at the stats behind this in the table. If you look back at traditional data, what I've called bad are DEA scores with a value less than 0.7, and you see the overall average of these balls. It's in most cases, it's less than 100 of average. And when you get the batted balls, the DEA scores about batted ball over 0.7, you see through the 10 different random samples that the average is very, very high. So it seems the DEA score seems to correlate very well with the probability of a hit. A next step for me would be almost naturally to do some correlation with that scores and the batted ball in play, the BABIP, the batted average on ball in play, and the DEA scores, because it seems to work very well for now. You have something that if it's higher than that value, you get a very bigger probability to get a hit of your batted ball. And the slugging, that's the same. The greater the DEA score is, the greater your chance of having a ball hit as a line drive and with a lot of distance. So you think of all the doubles, the triples, the home runs in general. Usually they are assigned a very big DEA score. So having that on mind, so 0.7, that's the key information with that new variable today. So you want to have hitters that are able as often as possible to hit with a DEA score over 0.7. So I'll show you some statistics to end the presentation that will do these, that will show you the DEA score versus a lot of different parameters. Just to have a feeling, I have not used all the hitters, so it's a sample of 153 hitters to what I'm showing you today. I have the information about all of them, but I have used only hitters that have at least 300 at-bat, in-play at-bats. So you see the distribution of the, so every, to understand this, every at-bat, you get a DEA score. Now I'm showing you the median of these scores for every hitters. So, you know the median. So Freddie Freeman, that is in my database today, the hitter with the highest median about the DEA score could be considered in that database, in that sample, as the more efficient hitters. So he is the one every single time that maximizes the quality of his batted ball. And on the other hand, Gene Segura last year seems to have been one of the worst. We know the story about him, so because it's very low with, versus the other people in the data set. So the 59, you need to interpret that for every hitters, 100 exists. So 100 or 100 score exists for every hitter. So the programmation is able to look and to confirm who are the best batted ball of the year for every hitter. So Gene Segura got some 100 batted ball as well. But the problem, if you look at the median, more than half of the time, the batted ball was 59% and lower than what he is able to do. And Freddie Freeman, on the other hand, 50% of the time, he was able to be to hit balls that seems to get to have balls that will get a DEA score higher than 73. Almost 74, and you are already in the area where the batting average and the slugging percentage is very good at that level. So more than half of the time when Freddie Freeman is on deck, if he hit the ball, more than half of the time he has a pretty good chance to make a hit of it. So once you get these DEA score for every single in play, now, if you remember all the information that is available via PITCHf and other source of information, now you are able to use the DEA score, that is kind of a new individual data, and do anything you're used to do, maybe otherwise. I don't know the secrets of all the teams, but if you're thinking of some testing you're doing, now you could retry these tests using the DEA score instead. And because the DEA score is not a normal distribution, naturally, it's if we use non-parametric statistical test, it will be we will get a way to generate p-value and do what we used to do about hypothesis testing. So the Kruskal-Wallis test is the appropriate test to use with the DEA scores. It's a non-parametric alternative to a one-way ANOVA, if you know about it. It's very useful here because it does not require the data to be normal, and it uses the rank of the data values rather than the actual data values. So now we will test medians as hypotheses, and I'll show you some examples. I have aggregated a lot of information on the same slides, but if you look back at all these scores that we get for every in-play batted ball, and now you want to check, okay, for a given hitter, is there significant differences between a left-handed pitcher or a right-handed pitcher? And in the data set I've used 153 batters. You see the distribution of the p-value, and you look at on the far left the ones that are significant at less than 5%, so traditional p-value mechanics. And in my samples of 153 batters from 2014, 15% of the hitters got significant differences between right-handed or left-handed pitchers. So I know there's a lot of things about platooning batters. So when you construct your lineup, there's some specialists. So it looks like it makes sense statistically for 15% of the hitters in the MLB. The other ones, we don't have yet statistical significances about it, but it's 15% of hitters with a p-value less than 5%. It's 22% if you get that alpha level at 0.10 instead. So, and once again, you have Freddie Freeman and Jonathan Scoop that pop up, that was listed in the last slide. So for every hitters, you could go back to the detailed results and understand, okay, how exactly is that difference? And so for Freddie Freeman, that show as a very good, efficient hitter. He even have a split, if you want, between left and right-handed pitcher. And this will show you that he is doing even better with the right-handed pitcher. It's a significant difference. He's pretty good already with left-handed pitchers, but if you need to manage, your bullpen, it would make sense for him to reduce the probability of a good batted ball by calling a left-handed pitcher against Freddie Freeman. On the other side, Jonathan Scoop is very bad about efficiency in the sample set, but it's even worse with left-handed pitchers. So at least for now, waiting at him to improve, we should make sure to expose him more to the right-handed pitchers. And the last thing to show today, because now it's time for me to conclude, it's do similar testing, but against the zones, the pitch location. So in the data set, we have information about the zone. These data, by the way, I was using a baseball savant to extract the information. And now about zones, a lot of hitters have weakness, if you want, zone by zone. So 37% of them got a p-value about zone that was at less than 5%. So there are significant differences. And almost half of the sample showed significant differences by using an alpha level of 10%. Because it's separated by zones, now you get a very small sample size, so it's not easy to get very low p-value. So I think the alpha level at 10% is a good practical alpha level. And once again, I pinpoint some hitters, and what is the information that is available now. Freddie Freeman, for example, again. Now the zones at the right, on the top of the slide, you have the meaning of the zones. It comes from the Baseball Savant site. And you see for the zone number 5, for example, for Freddie Freeman, the median in that zone is at 82, so it's very, very good. And you can pinpoint, you can see a lot of different things. So you are able to know in more details what are the zones where the hitter is very efficient and what are the zones where the hitter is very inefficient when compared to what he is used to do as a batted ball. And Justin Upton and Joe Mauer, to conclude this today, it's very interesting. Justin Upton, the zone 11 that is outside the strike zone, is very weak. So if you want to waste a pitch, that's a very, very good location for him, because if he hit the ball, it should be a very weak batted ball. And Joe Mauer, there's no significant differences. So you see he is a kind of a complete batter. So to conclude, there's, I think, several applications possible. We can discuss it. I will not explain this in details. I don't have time for this, but for sure, that methodology, I think, with the Statcast data that will come up, PITCHf, HitFX, it could be very, very interesting to blend a lot of inputs and outputs together and generate a new variable that might be more useful to do some statistical analysis. So thank you. Questions, comments, I think it's too late, but I'll be around so I can answer you personally all the time. Thanks.